In addition to having a horizontal and vertical component, of course, we could add that sideways component, that crosswind, which would give us a three-dimensional problem. So to do this, it's best to begin with acceleration equation and use integration to work our way up to the velocity and position equations. And that's because this will be a little bit more complicated than the one we were doing with 2 dimensions. Okay, so let's see what happens here. We have a golf ball that's hit due east with initial velocity in meters per second of 50, 0, 30. A horizontal crosswind blows south, producing an acceleration of 0.8 meters per second squared. Find the equations of motion R of t, V of t, and A of t. And we're actually not going to do it in that order. So, all right, let's see here. So this is up. This is north, if you remember on your compass headings. And this is east, because this is the x-axis. Right, so this is x, this is y, this is z. Z would be up. This would be north, and this would be east. Okay, so a golf ball is hit. Golf balls are always hit from the ground, so that's easy. So the golf ball starts here, and it's hit, and it heads due east. Like that. Right? It's going to end up over here. Okay, so let's look at the acceleration vector. Let's start there. So the acceleration vector would be the accelerational forces acting upon the ball, which there's no accelerational vector in the x direction, but there is acceleration in the other 2 directions. Now, the wind is producing an acceleration of 0.8 meters per second squared, but it's blowing south. So if you see that. Okay, so let me kind of give an arrow for the wind here. So it's blowing to the southward direction. So your wind is right here. Right? That's the wind. Blowing southward. And so since it's blowing southward, that vector would be negative, right? So it's a negative 0.8 meters per second squared. And then because of gravity, we know, and this is metric, I'm right on this one, this was metric, so this is a negative 9.8. Now keep in mind, this is due to the wind right here, and this is due to gravity right here. Okay, so we have our acceleration vector done. And for the record, this would be meters per second squared as its unit. All right, lovely. Now, how do I find velocity? Well, velocity is the integral of acceleration with respect to time. So that would be the integral of 0, negative 0.8, negative 9.8 with respect to time. So velocity would be 0, because the integral of 0 is 0, and then negative 0.8 t and negative 9.8 t, plus some constant vector. I'll call it C1. But we know that constant vector. That constant vector is our initial position. Oh no, excuse me, initial velocity. Excuse me, our initial position was 0, 0, 0. I better make a note of that really quick. Okay, because it's a golf ball, so golf balls in general are hit from the ground. So the initial position, if you remember, is x0, y0 is 0, 0. Let's write that. Now, what about the initial velocity? Well, the initial velocity is right here. They tell us the initial velocity right here. So we have it. Right? This is u0, v0, w0. Initial velocity. Okay, so because of the way projectile motion works, this component here will be the initial velocity. So that would be 50, 0, 30. So we have our velocity vector. The velocity vector would be 0 plus 50, so 50, negative 0.8 t plus 0, negative 9.8 t plus 30. And that would be meters per second. Now, if you're thinking, hey, this part's looking familiar, yes, it does. It works very similarly to two dimensions. It just has this third component where we have this crosswind. So it adds some difficulty here. All right, now what about position? Well, position, of course, is the integral of velocity with respect to time. So we're going to integrate 50 comma negative 0.8 t comma negative 9.8 t plus 30 with respect to time. That will get us 50t negative 0.4 t squared, because we would add 1 to the power and divide by that new power, and then negative 4.9 t squared plus 30t, and then plus a constant vector, but that constant vector would be our initial position. But the initial position was 0, 0, 0. So therefore, there's nothing really to add. So r of t is equal to 50t negative 0.4 t squared negative 4.9 t squared plus 30t, and that would be meters. Done. I just thought I might want to throw in that initial velocity vector. It's doing something like that. Right, there's your initial velocity. Oh my goodness. I forgot about my third component here. So I was so worried about trying to fit it in that, here, let me put it this way. 0, 0, 0, because it's x0, y0, z0. Sorry, there's three pieces there. All right. Now, let's find the time of flight. Okay, so the time of flight is the time it takes till the ball hits the ground. Okay, now it hits the ground at z is 0. Right. So what we really want to do is take the z component, which is here. The position is z, x, y, z. Oh, let me label that here. This is x of t, this is y of t, and this is z of t. That notation that we learned earlier in this section still holds true, and it's going to hold true in later chapters as well. So we want to take the z component, which is z of t, which is negative 4.9 t squared plus 30t, and we want to set it equal to 0 and solve. Luckily, this one's really easy. They both have t in them, so you could take a t out, and it leaves you negative 4.9 t plus 30 equals 0. So either t equals 0, well, oh no, duh, right? So it started off at an initial position of 0. So z was 0 at the beginning, so right there, so that's easy. Or t equals, and whatever negative 30 divided by negative 4.9 would be. And of course, I can just do that math in Maple, or I could actually use the solve command and tell it to solve it. So I could say, hey, take negative 30 and divide it by negative 4.9. That would also get me 6.122. So either way, I'm going to get 6.122. That's the time of flight, because it'll land at 6.122 seconds. All right, so I know it hits the ground, 6.122. So then it says, where will the ball land? So that's asking, it's coming out this way, woo, and it's going to go down. So where will the ball land? I guess I should have put arrows on this. So it's not finished, it's carving a path. Okay, so where will the ball land? That's position. right? So what it's really asking you is, hey, what's the position function at 6.122? Right? I know what the z component is going to be. The z component is going to be 0, or it better be. But what about the other two components? So that would be 50 times 6.122. That would be negative 0.4 times 6.122 squared, and then 0. All right, let's find those values. Let's also prove that it basically came out to 0. Now, there's a few ways to do this. I mean, I could just take 50 and multiply it by that value, and then I could take negative 0.4 times that value squared. Sure. But why not just name my position vector right here? So I called it R6. You can see it's coming out as a vector. And then I said, hey, evaluate R6, and then I just copied and pasted that answer at t equals 6.122. And you can see it's 306.1, negative 14.99, so roughly negative 15, and then 0. So 306.122, negative 14.99, 994, 0. So you can see that it was blown off course, right? So it's landing, z is 0. So this is the part, oh, and for the record, this would be meters, right? Meters. All right, so there's the position, which it asked for. All right, so this is because it landed. This is in the x direction because it was blowing, right? So you're trying to shoot it straight east, right? You're aiming east, right? So aiming east, right? The shot was made straight east. Sorry, my E is looking weird there. I'll just east. There we go. But this is because of the wind. Because of wind, it was blown off course. And ended in the rough. So blown off course because that wind is pushing it that way. So it ends up with a wide direction that's negative because it's getting blown to the south. So that's what we're showing with those vectors.